Good morning, good afternoon, good evening. I'd like to take this opportunity to give some good news to you all. I'm very pleased to announce that once again, we will have the workshop proceedings, and they will appear in Journal of Singularities. I'm honored to call David Massey, the editor-in-chief, to join us now. Good morning, David.
Good morning, good afternoon, good evening, whatever. Yes, it's our great pleasure. I consulted with the managing editors, Victor Gorionov, Paulo Alufi, and Javier Babadia, and we all agreed it would be a great honor to publish the 30th anniversary proceedings of the workshop. It's quite an event.
Thanks to many people. The workshop has been a channel of dissemination of important works on singularity theory, and there is no doubt that JOS has been a great partner in that matter. So we are very pleased for having this. Sorry?
No, I'm saying we were very pleased. So
thanks.
Please go ahead.
No, just say that we feel very pleased to have this support once again. Then, right, we celebrate the 30 years, as you say.
Yeah.
And so thanks to all the editors of the journal, and a special thanks to you, David, for your contribution to the workshop and for so much attention for joining us today.
Oh, well, you're certainly welcome. And we look forward to publishing the proceedings in this weirdest of years. It's
great.
Yeah, I'm glad that the workshop found a way to go on somehow. So
yeah, I'm glad too. Okay. Thank you very much.
All right, you're certainly welcome. Have a great rest of the conference.
Thanks. We will now have another countdown for the first talk of this morning. Thank you all. It's a great pleasure for me to introduce my friend Wojciech Domitrz from Poland, Warsaw University of Technology, and he will speak about singular improper affine spheres from a given Lagrangian submanifold. Thank you so much, Wojciech.
Thank you, Miriam. Thank you very much. Can you see my screen?
Just a second. Yes, we can now see it. Yes.
Okay. Yes. Thanks. First of all, I would like to thank the organizers for giving me opportunity to have a talk on this nice conference. It's very well organized, but nothing can beat the real San Carlos conferences. Everybody must agree that everybody, of course, miss the real San Carlos conference in the real life. I have a great pleasure to have a talk here because my collaboration with many people started from San Carlos conference. I meet here many people, among them a lot of very good Brazilian mathematicians like Sidinia, Pedro, also Miriam. We have collaboration with Miriam and Pedro. I will talk about result of this collaboration even during this talk, and also Roberta, and also Marcos Kreiser, who is not from San Carlos, but also he's a Brazilian mathematician. So I'm very grateful for this conference to meet these very nice mathematicians, not only from Brazil, from all over the world. In Polish, we say that we have such saying that every road is going to Rome. And now I see that every singularity road is going to San Carlos. Okay, so I will start now. I will talk about singular improper affine spheres from a given Lagrangian submanifold. It is the joint work with Marcos Kreiser from PUCI and Pedro Rios from San Carlos. but also I will talk about another results with Brazilian mathematicians, which goes to this result. Okay, so what is improper affine sphere? To define improper affine sphere, I first must define a affine normal vector field. I hope that you see my pointer. Okay, so if we start with the immersion from the m-dimensional submanifolds to Rn+1. So the image is hypersurface. And on Rn+1, we have a canonical affine connection, flat canonical connection. And we assume that we have a vector field which is transversal to the image of phi. And phi then defines a connection on U and a symmetric bilinear form H on TU by this equation. This is classical equation. X and Y are vector fields, move vector fields tangent to U. Okay, by this equation we have we defined H and we defined nabla. Okay, this connection. And we have also, we can define also two volume elements. The Ni H, which is usually defined in the usual way from this bilinear form H, yes, and the other one we defined in such way that we take the usual determinant on Rn+1 of the vector fields, and we put on one position this vector field psi. Okay, then it is the result due to Blaszke. There exists a unique up to sign transversal vector field psi such that these two volume forms agree and they are parallel with respect to this connection defined on U nabla. Okay, and we call psi affine normal vector field or Blaszke normal of this hypersurface which is included in Rn+1. Okay, and what is improper affine sphere? A sphere is defined in affine geometry in the same way like usual sphere. So a hypersurface in Rn+1 is a affine sphere if its affine normal lines through each point of phi u intersect at one point. This point is of course called a center, but there is also one more case. There is a possibility that all these affine normal lines are parallel, and when such a sphere that have a center at infinity is called improper affine sphere. So this is improper affine sphere. Otherwise, if the center is not infinity, it's a point, then this sphere is called proper. Okay, so first one who studied affine normal is Abel Transon. He was a French mathematician, also utopian socialist, Saint-Simonist. And he defined it for a curve in 1841. So we have a curve. We have a point on this curve and a tangent line. And then we take the parallel to this tangent line and we take the middle points of them, because if they intersect our curve, yes, they intersect our curve in 2 points, and we take the middle points, and these middle points are built a curve, and we take the tangent to this curve, and this is affine normal to this curve at this point. Affine spheres were first defined by George Tsitseikas. I'm not sure if I pronounce well his name. He was a Romanian mathematician, the founder of Romanian School of Geometry. And he first defined affine spheres around 1908, 1909. It's also, as I already mentioned, it was studied by Wilhelm Blaszke. He wrote a book in 1923. Wilhelm Blaszke is a famous Austrian mathematician who worked in Munich. And also it is as you see, improper affine sphere are related to the Monge-Ampère equation. So there are two great scientists, French scientists, Monge, who is the founder of differential geometry, the father of differential geometry, and also descriptive geometry, and also Ampère, a great physicist who is the founder of electromagnetism. Okay, so how they are related? How the improper affine spheres are related to the real Monge-Ampère equation, the classic Monge-Ampère equation. So we know that for the improper affine spheres or affine normals are parallel, so we may assume that they are vertical. So we assume this affine normal is this vector 0, 0, 0, 1. So it's a vertical vector field in Rn plus 1 for the canonical conjunction. Then we have the proposition, a graph of a smooth function f when U is open subset of Rn, so the image, so the graph of this function defines a hypersurface, is the improper affine sphere with the affine normal xi, if and only if it satisfies the Monge-Ampère equation. The determinant of the Hess matrix is equal to constant. Okay, so and what is known about it? There is a result by Georges Calabi-Pogorelov, and it states that if this function is strictly convex smooth function satisfying this equation with c equals to 1, so when f is quadratic polynomial. But there are also another improper affine spheres, but they are not smooth, they are singular. I think I will put them in a symplectic terms. I think first one who studied them and used this language was Go Ishikawa, and with the paper with Mashida. And let us assume that we have an open subset of Rn with the canonical symplectic form omega. Omega is the canonical symplectic form dxi plus n. And then we have a function f. This is a smooth function on V, on this open subset. And then let yf be a Hamiltonian vector field. Hamiltonian vector field is dual with respect to this symplectic form to the differential of or minus differential of this function f. So if we take the inner product of this vector field with the symplectic form, we obtain just one form. And this one form must be equal to the minus differential of f. And then in the symplectic language, f satisfies classical Monge-Ampère equation, this one which I defined before, the determinant of the Hess matrix, Hessian, is equal to constants, if and only if the determinant of the differential Jacobian matrix of the Hamiltonian vector field with the Hamiltonian f is equal to constants. Okay, and how this improper affine spheres looks in the symplectic terms. Okay, let's assume that we have U, the open subset of R2n, and let an immersion phi be a transversal to this vector field xi, yes, 0, 0, 0, 1, yes, and this R2n carries a symplectic form omega. Then this phi r could be written, the first component which goes to R2n is xr, and fr is the component of r, yes? And then we assume that xr is locally invertible, and we define the function fr is just the composition of xr with this function f for some function f on V. Then yfx is the Hamiltonian vector field as we defined before, and which defines by the Hamiltonian f, and we have yr. It's just the composition of this xr, of this first component of phi r with with the Hamiltonian vector field of big F. And then we have such a matrix, which is defined by this equation, in which here is the Jacobian metric of XR and the Jacobian matrix of YR. Yes, this we have the matrix AR. And when in this setting, phi of U is an improper affine sphere with this affine normal 0, 0, 0, 1, if and only if the determinant of this matrix A is constant. Then we have also on I will define the symplectic structure on the tangent bundle. We know that there is a canonical symplectic structure on the cotangent bundle, but now we assume that there is a symplectic form on V. Yes, V is an open subset of R2N, and omega is the canonical symplectic form on V, on R2N, given by the dxi I plus n, which we defined before. And then we have the map flat. This map is an isomorphism between the tangent bundle and cotangent bundle on V. Yes, this in fact says that the omega, the form, is non-degenerate. Yes, it's really symplectic. Yes, this is isomorphism. This isomorphism flat. And on T star V, we have a canonical Liouville form, which gives the differential of this Liouville form gives the canonical symplectic form of the cotangent bundle. So here we have already on T star V, we have already a symplectic structure and one form, canonical Liouville form. Yes. Then, if we take by this map flat, we take the pullback of the differential of alpha. Differential of alpha is a canonical symplectic form on cotangent bundle. Then we obtain a symplectic form on the tangent bundle. Also, we can define the contact form on TV cross R. So it, in fact, this is the space of one jets of function on V. Yes. How we can define it? We take just on R, on this R, we have the coordinate Z, and we take the form dz plus pullback of alpha of a Liouville form by flat. Yes, when this is a contact form where Z is a coordinate on R, as I said before. And then, if you have a function F, smooth function, and its Hamiltonian vector field, yes, then the map L tilde, which goes through V, and maps X to X, the Hamiltonian vector field of X, and F of X is a Legendrian immersion to the contact space TV cross R. So it means that this goes to the kernel of the contact form. Okay. And then, using this construction, we can define two types of improper affine spheres. These two types of proper affine spheres, they are only defined for these are even dimensional improper affine spheres. In the dimension 2, this is the only two constructions that exist. But in high dimension, as I will show you, there are many constructions, but this construction, a generalized construction, which we have in dimension 2. For general even dimensional spheres, this construction was defined by Cortés first, the Spanish mathematicians. Okay, so we have U1 and U2, two open subsets of Rn. S are coordinates S1, S2 on U1, and T are coordinates on U2. And beta and gamma be two Lagrangian embeddings to R2n with the canonical symplectic form omega. So it means that they lies in the kernel of the omega, the tangent spaces if you restrict a form. In fact, what I should say, if you take the pullback of symplectic form to U1 by beta and by gamma, you obtain 0, yes? And the dimension of U1, U2 are n, so it's a maximal possible dimension in such a case. And lambda 1 is the image by beta of U1, and lambda 2 is the image by beta, by gamma of U2. And we define two maps. The map X, which this is a map from the product of U1 and 2 to R to N. And this is just, you take the arithmetic, yes, beta S plus gamma T and divided by 1/2, yes? And the middle points from beta S and gamma T, in fact. And U2 and Y goes also from the product of U1 and U2 to R to N, and you defined in a similar way, but instead here you have minus instead plus here. Yes, you have a minus gamma T minus beta S, 1/2. Yes, and beta and gamma are Lagrangian, so they satisfy this equation. As I said, if you take the pullback by beta and by gamma of this form, of this form omega, you obtain 0. Therefore, we have these conditions. Yes. And then, of course, we have these conditions satisfied. This is because the omega is a two form. So if you change the order of the arguments, you obtain minus. So if you have a minus here, so this is okay. And then we have this equation. From this, we get that there exists a function f that satisfies these two equations from I equal to 1 to n. There exists a function f. Yes. And when we have this function f, then we can take the matrix k to n minus identity on n minus identity 0, 0. Yes. So we have here minus 1, 1, 1, 1, then 1, 1, 1, 1, then 0 and 0. And assume that the tangent space of lambda 1 and beta s and of gamma 1 and gamma t are transversal, then the immersion phi s, which we defined like this, it's x st, yes, we defined on the previous slide, plus f st, this function that we showed that there exists such function that satisfies these two equations. Maybe come back, I show, yes. This is the equation that should be satisfied, yes, by f, and this is the form of x. X looks like this, yes. And then this function is an immersion with the matrix A, which we defined on the previous slide, of this form, k to n. As a consequence, the image of this is an improper affine sphere with the Blaschkel normal 0, 0, 0, 1 by the previous theorem. And there is another construction. Now we do not start from the two Lagrangian submanifold, but we start with the holomorphic map. This holomorphic map, yes, H of Z, yes, is defined on Cn, yes. It goes to C, yes. P denotes the real part of this map, and Q denotes the imaginary part of this map. Then we have this coordinate Z, yes, S plus IT, yes, this is the components of these coordinates, and the Q of the S denotes such a gradient with respect to S, and the Q of the T denotes the gradient with respect of T. And we define a map X of T, which is x1 f of t, x2 f xt, and this is x1 is just s, and x2 is just dq over dt. And y st, which also has two components. The first component is t, and the other is dq over ds. And then we defined f of st, which is q of st minus the sum from k equal to 1 to n, tk times dq over tk st. Yes, then this map, if you take such a matrix, J to N, we have 0, 0 on the diagonals, yes, and then we have the identity matrix and minus identity matrix in these places. And if you assume that we have such a point as T, that determinant of the Hessian with respect to the t variables is not equal to 0, then the map phi st, xt, st, fst is an immersion with this matrix A, which we defined previously, is exactly of this form, yes? And the image is improper and affine sphere with this normal. So we have two construction of improper affine spheres. Of course, this is not the only cases in the dimension higher than 2. Yes, if you take n equal to, so we are in dimension 4. So then, if you take such a matrix and such a map F, then, but A is not similar to K4, no, neither J4, and XF is neither center-chord nor special. Yes, neither of these two constructions. First one was called center-chord, the other was special. And if one consider the product of the center-chord chord and improper, special improper affine spheres, then one can obtain new construction of improper affine spheres. But in this talk, I will study these two constructions. And then we show with Marcos and Pedro that any germ of simple stable Lagrangian singularity is realizable as a center-chord improper affine spheres. Because we assume in these theorems, in these previous theorems, that these points are smooth. Yes, but if we drop this assumption, yes, then we have singularities, and these singularities are simple stable Legendrian. We can realize any simple stable Legendrian singularity as a center-chord and special improper affine spheres. So we somehow know how the singularities of improper affine spheres in these two constructions looks like. This is just Legendrian singularities. Okay, so let's look at some example. But now we will start. We start with center-chord improper affine spheres, but instead of taking two Lagrangian submanifold, we take the same Lagrangian submanifold 2 times. Yes, let's assume that that we are in the case on the plane, so every curve is Lagrangian on the plane, and we take just a circle. Yes, a unit circle. Then we define the map X starting from this construction, which I defined before, has this form, and Y has this form, and F has this form. We repeat this construction that I explained before. Okay, and this is the image of the center-chord improper affine sphere starting from the cycle. You may say the cycle is here, yes, and the cycle is just the capital H, yes, and there are also 2 isolated singularities, and of course it goes further and further. Yes, you can repeat this construction, and the same construction you can do for improper affine spheres of the type special. You take also the cycle, but now you take it in a complex. Z is a complex variable. Yes, then L is a unit cycle in the plane. Yes, and we have this map is X, Y, and FST is defined in this way, and then this is how it looks like, this improper affine sphere starting from this. Yes, here we have the capital H of cycles. There are singular points of the type of capital H. In dimension 2, it was proved by Ishikawa and Mahida that what you can obtain is the generically say capital H and swallowtail. We cannot see now swallowtail yet, but we will see if we, instead of a cycle, we take an oval. Yes, we take an oval, and then we have here, this is the projection of the set of singular points of this improper affine sphere on R2. Yes, this set is in fact studied by many people. It's called the Wigner caustic. How it appears: you take the points which have parallel tangent lines. Yes, you join them and you take the middle points of them. Yes, and this is just the locus of these points, of the middle points of the points. We have a parallel tangent lines with parallel tangent lines. Okay, so how it looks like this improper and fine spheres. So we have here, yes, we have also this set, this curve itself. It's a set of singular points of improper and fine spheres. But how it looks like, you see here, yes. Maybe it's not visible on this picture, but here in this area we have a 3 swallowtails. Each cusp is responsible for 1 swallowtail. Yes, so maybe here is more visible that we have these swallowtails. Yes, they are very small comparing to this curve. Yeah, therefore maybe they are not well visible. Maybe here is better. You can see that this is the swallowtail. Of course, you can repeat also this construction for the special improper and fine sphere starting from this oval. Yes, this is how it looks like. But there are also some other points, maybe some other singularities, may be more interesting even if we consider the curve which is not oval, which have inflection points. Here is the example of such a curve. Yes, and we repeat the construction of center-chord improper affine sphere. Yes, when you see here, this is the points, here and here, there are points which are responsible for the inflection. Yes, and you have something like here above, or maybe here it's better seen. Here are the points which are inflections. Yes, the image of these points which are inflections. Yes. Here you have a more complicated curve. Yes, so the curve is dotted. Yes, it's dash line. Yes, dash line. This is the curve in black, and I show only these components which are going from one inflection point to the other inflection point. This is the components which are projection of the singular set of the improper affine spheres. Yes, to the plane. Yes, and there are also other components, but the picture will not be visible if we put all of them. I only put these components which are responsible which started from the inflection point. If you have such component which started from in one inflection point, it's end in the other inflection point, but not always to the closest one. Yes, as you see, if you start, for example, here, you finish here. Yes, if you start here, you finish at this point. But what we can prove? We can prove that the number of inflection points between 2 inflection points which I joined by a component of this set Wigner-Kostyk. So this is the Wigner-Kostyk is the singular, is the projection of the singular set of the front. Yes, on R2M. Yes. They connect 2 inflection points, when the number of inflection points between them on both, on this branch of the Wigner-Kostyk joining, and also on the curve, yes, between them, the number of inflection points are always even. Also, we can prove also something about the cusp points. You see, if you consider, for example, this part of the curve, yes, between inflection points, then you can see that in this how it behaves. If you take the whole curve, the branch with joining 2 inflection points, and then the part of the Wigner-Kostyk, yes, the branch of the Wigner-Kostyk joining 2 points, then you can see how that at this point this branch going smoothly to this part. But they are not always going like this. Sometimes they are going like this, that you have cusp and they go this direction and then this, and it goes smoothly. Sometimes you have something like a point which is tangent, but you change the direction. And it depends. If you have the same behavior at this point, symmetric behavior, you may say, when the number of cusp points on this branch joining two inflection points is even. But if one point, or for example, this branch, if you have this branch, you start like this, you go there, and you come this somehow from the other direction. When the number of the caustics is odd, so we can prove it with my PhD student Wojciech Domitrz, these two results, and how the special improper affine spheres looks like for this curve with inflection point. The first example, yes. So this is, it looks like this, yes. And we want to study the singularities of this improper affine spheres, this I may say the new singularities, which coming from the inflection points and behaviors like this, when you assume that you're starting from the object which is not convex. Okay, so I fix the notation. So now omega, the symplectic forms is dqi dpi. When the big omega on tr to n, the new coordinates I just in the fibers of the tr to n I denote by p dot and q dot. Yes, when the form by this formula which I described have this form. Yes, and the contact form which I described on the one jets or tr to n cross r have the same coordinates like here on tr to n, and this coordinates was z like before. Okay, and in these coordinates we have Lagrangian and Legendrian maps. Lagrangian maps which we project on R to n, and Legendrian which we project on R to n cross R, which we project on Z. Yes, yes. When Lagrangian map, we have Lagrangian immersion to this space, and Legendrian immersion to this space tr to n cross R with the contact form. Yes, and we have these two projection. Yes. Projection R to n from tr to n, and p tilde projection from tr to n cross r to r to n cross r. And this is the Lagrangian maps. Lagrangian maps, yes, which is just pi composing immersion composing with pi, and Legendrian map x, y, f composing with pi tilde, which goes to r to n and r. So the image of this Legendrian map, yes, is just this improper affine sphere. Of the front of this, sorry, not Legendrian map, but the front of the improper affine sphere is a affine sphere. And we have, if you have Lagrangian and Legendrian map, you have a generating function, yes. This generating function has the form, yes, R to n from q dot goes to g q dot, and we can describe then using this generating function Lagrangian submanifold in this way. Yes, p dot is equal to partial derivative of g with respect of q, and p is equal to partial derivative of q dot, yes, with respect of q dot. And then we have Legendrian submanifold q in the coordinates qp q dot p dot z, and they given by the first two equation the same. Yes, this is not two, in fact it's 2n equations. Yes, and one more equation, z equals to this function g on q dot minus q dot p. This is standard construction of the generating function for the Lagrangian, how to construct from the generating function Lagrangian submanifold and Legendrian submanifold. Okay, but sometimes this is the case when this previous case is the case when you have this, your Lagrangian or Legendrian submanifold is transversal to the fibers, but it's not always the case. Not always we need to have a case when instead of generating function we have a generating family. Yes, it means that we need some more coordinates. Yes, some parameters, some coordinates that will give us this generating family, but in the bigger space. Therefore, and when we intersect and project them, when we have extra equation, we have extra parameters beta, yes, and we assume the GB over the beta is equal to 0, and the previous equation are the same. So this is the same case here, yes. We have Z for the Legendrian, but also we have this equation, the G over the beta is equal to 0, yes. And the generating family can be obtained from the generating function in this way, yes, in this way. We want to have the projection on PQ parameters. Okay, so how the generating families look like for the improper affine spheres if we start from the one Lagrangian submanifolds, yes, for the center-chord improper affine spheres. So if we start from Lagrangian submanifold defined in this way, U and the differential of S, this is Lagrangian submanifold, yes, with the generating function S. Then this generating function for this construction that we preserved has this form. And what we may see? We may see that this function is odd in Q dot, yes, and the generating family has this form using this construction, and you see this generating family is odd in beta. What I mean, if I replace beta by minus beta, I obtain minus GC beta QP. Yes, if I instead of beta here put minus beta here and minus beta, so plus beta, and here will be plus, so I obtain this function is odd. Okay, and how it is? How it is for the special? What construction we have for the special starting? For special, we can have also the same construction, yes. So the generating function is this, it's just this Q, which is just the imaginary part of the function H, yes, of the function complex holomorphic function H. Yes, when the generating family, we have the same construction, yes. But if we assume that our function, holomorphic function H, has this property, that H of Rn goes to H, it's a real holomorphic but real function, it maps the real points to the real points, yes? So it has this property, yes, yes. So then it implies that this function Q is also odd in beta, yes? So this generating family for the special improper affine sphere is also odd function in beta. So in both these two constructions, we have odd function in beta. And then we have Z2 symmetric in fibers Lagrangian submanifolds. Because if we start from these old generating families, the generating the Lagrangian submanifold that which we obtain will be odd in function. What I mean not in function, if you odd in fibers. What I mean by this, if I replace the parameter in the fibers by minus k, yes, then the point is also belongs to this Lagrangian submanifold. So we have a Z2 action in the fibers. And then if you have a Z2 action in the fibers to classify such Lagrangian submanifold, we of course need a odd diffeomorphism, a special Groth action. So this diffeomorphism must be odd in fibers. Therefore, we have such definition that these two generating families are Z2 symmetric Lagrangian submanifolds are germs are R odd equivalent if there exists this such usual formula, yes, but we assume that our diffeomorphisms in fibers are odd, yes, and we have the theorem on equivalence that Z2 symmetric Lagrangian maps are Z2 symmetrically Lagrangian equivalent if and only if they odd generating families are fibered odd equivalent. This to prove this result, we need to use we use just the usual method described by Arnold by adapted for the Z2 symmetric equivalence. Okay, so for this now, so we reduce the problem of the classification of this of the singularities of this improper affine spheres. For the special case, we started from one Lagrangian submanifold to the classification of the odd functions and their odd unfoldings. Yes. So we, for this, what means the function is odd? We means that you put minus in every coordinate when you obtain the same. It's even, sorry. This function is even. If odd, if you put minus, you obtain minus. Yes. And it's worth mentioning that if you take the ring of even function, this is the ring. Yes. But if you take the odd functions, this is not a ring. This is module over a ring functions. Yes. Then for this, of course, we need to use odd diffeomorphism, yes, and we say that two functions are equivalent, yes, that two odd functions are equivalent if there exists at odd changing of coordinates of diffeomorphism, which map one to the other. Of course, we have to find the tangent space to the R orbit of odd function at this point, yes, and it looks like this, yes. So you take the function g and differential with xi. It's not anymore odd. You have to multiply by all xj, and this is the tangent space. Yes, and of course, what odd diffeomorphisms, odd are foldings in our case. So we have a function which you restricted to put 0 the parameters when you obtain f just. So this is the odd deformation, but you assume that this function, if you put lambda, any lambda fixed, when you obtain odd function. This means that this deformation is odd deformation. Yes. Okay. And then this is the result of our joint cooperation with Miriam, Manuel, and Pedro Rios. Yes. And we obtain just how the key parameter deformation of odd when it's of odd versal, the condition. This it's not very difficult result because this odd diffeomorphism, it's a geometric group in the sense of diamond, so the machinery is ready for the classification. Yes, so this result, it's not difficult to obtain. Okay, and of course we have the equivalence of odd deformation. Yes, the equivalence of deformation looks similar to the normal one, but we must remember that we have to use odd diffeomorphism, yes, in X. Yes, therefore it looks, this is the classical definition, but we must remember that we are in an odd category. We also have a result about determinacy of when a germ is finitely determinated. Yes, we have very similar result. We only must remember that this in this model we need in this idea we need to odd function only. Yes, and now how the classification looks like. Yes, so if you have a submersion, so this is equivalent to just x1 submersion to R. Yes, if we have a singular point, yes, and the dimension of the space is bigger than 3, bigger equal 3, but there are no R odd simple manifolds. You remember that you add the quadratic form in the usual formula for M starting from 3, but the quadratic form is not odd. You cannot add it, just simply saying why it is so. And then we have a classification. Yes, this is also our result with Miriam and Pedro. We have such singularities, we call it A to K by K, because codimension in fact is K. Yes, but it looks like 2K singularity, but we divide it to 2. So we have only the odd from this, and this is how the odd deformation looks like. Look, there are only odd powers, and this is for first case. For the dimension 2, we have D to K by 2, E8 by 2. Yes, so this is this which are odd. Yes, and we have also someone which are not simple. It's a J plus minus 10 by 2. Yes, J10 is not simple, but in this category it's simple. It looks like this, and E12 by 2. Yes, so you see this is K, this is 4 codimension, this is codimension 5, and this is codimension 6. And via versal deformation looks like here. So we have the odd powers, yes, in this versal deformation. And what is the relation between generating families for these two constructions, for the center-chord and for the special one? The relation is simple. If you started from SK, yes, first of all, I must mention that in the case of special improper affine spheres, we start from the holomorphic function. So we need here start from analytic function, yes. So we are in the analytic category in the special improper affine spheres. So we started from analytic function of this form. Then we have holomorphic function replacing by just real S by complex Z, yes. And then we have such relation between generating function center-chord and special. You here multiply by I, the Q dot, and taking minus I in 4. So this is the relation between them. Yes, so if we have a result for one, we have the result for the other. Okay, so what singularities can be realized for the improper affine spheres, center-chord, and special one? Not all of them, which are simple, are realized. Only A to K by 2 and A4 by 2 for M equal to 1 are realized. So it means if we started from the curve on the plane, if we started from the surface, then this is this singularities I D plus minus 4 by 2 and D plus minus 6, this one here up to 8 by 2. Yes, these are realizable for both center-chord and special. The other, which started from simple, are not realizable. There are not enough parameters to realize them. Okay, and this is the condition when they are realized. So if you start from the function with the fed differential at 0, it's not equal to 0, so you have A22 singularity. If you start from the function with the fed derivative is equal to 0, but the fourth at 0 and 5 at 0 is not equal to 0, but at 0 you have A4 by 2 singularity. And now some pictures. When we started this classification, we thought that you should be done before. Yes, there are a lot of papers about Z2 equivalence of, but somehow we cannot find this result. But there is a relation to the previous result. There is a relation to the Janeczko-Robert result. I think in the beginning of 90s, they studied singularities, Lagrangian singularities, but starting with that I remember, and on the base there is the Z2 action. Yes. And then they discovered something which they call symmetric butterfly. It looks like this. And this symmetric butterfly appears as an A42 singularity for the special affine sphere, but this is a Legendrian case, not Lagrangian. Yes, and this is a Legendrian case. So this is the front, in fact, the picture of the front. It looks like this. Yes, yes. So this is symmetric butterfly. Oh, it looks like this singularity. And this is how it looks globally. Yes, the whole picture not intersecting this singularity. Of course, there are conditions for realization. Maybe I will skip it because they are a little bit technical and complicated in the formula. And I think I will finish this talk. Thank you very much and muito obrigado. The last paper which I talk about, the main subject of this talk, it's published this year in Advances in Mathematics. Here you have the address, how to get it. It's open access, so everybody can get it. Thank you very much.
Thank you very much, Wojciech. We can wait a little bit about possible questions. Meanwhile, I have a question. So I'd like, how to say that, when you have that theorem, I think it's a theorem with your PhD students, if I'm not mistaken.
Yes, yes, with Michał. Yes, I'm coming back.
So in that theorem, you have that the inflection points on both the branch of the Wigner caustic
Yes,
curve, it's an even number. Is that correct?
Yes, yes, yes. On each of them. There are the same number. Oh, sorry, maybe I will show the picture. That will be easier to understand. Okay, so you start from this point, blue one, and you go from here. Yes. Can you see my pointer?
Just a second, Wojciech. We cannot see your presentation at the moment.
You cannot see?
Now we can see.
Okay. So this is the you have, for example, you take what is the number of inflection points? So I mean inflection point, you have this blue curve starting at this point, this component of the blue curve, yes, this branch. Starting from this point, can you see my pointer?
Yes, I can.
And you go along this, okay, I will go like this. And you go here, yes, to the end, yes? So the number of inflection points of this curve is even. Also, the number of inflection points, if you start at this point and go along a curve, you go along the curve and you get to this point, the number of inflection points is also even. Yes, so you cannot join if you have, so the theorem is because you see, it's not always joined to the closest inflection point, yes? The number of inflection points between the beginning and end on the curve is also must be even. Yes?
Right.
Yes.
Okay, but then you start to looking at the improper affine sphere, and you recognize later, at least later in your talk, that you have that Z2 action.
Yes.
So my question is this the fact of this number being even? It should be related to that Z2 action, shouldn't it?
This I don't know, because we spent with Michał a lot of time to prove it, but the proof is somehow maybe it is, but I don't see maybe you're right, but I cannot see now in the proof. The proof is coming from the geometry of this curve, and it's somehow very. You look for the angel function. Maybe you're right, but I'm not sure. I cannot say you now yes or not. Maybe it's an interesting question if it's related, if you can get it from the Z2. But you see, this is I'm not sure. I have arguments for and for not, because this is a global phenomena, not a local phenomena. Okay. And this function, we always this phenomena is local here, but here is a global phenomena. Yes, somehow this inflection point here do not know about these inflection points. Yes,
right.
This is in fact the more important thing is here. It's because this Z2 action is local, not global, I think. So this is not. Probably not, but I cannot say definitely not, but probably not. This is global phenomenon.
But yeah, you are right. It's global versus local, so it's possible, but
it's locally. You have this Z2 action, but not globally. Yes.
So it was, as far as I understand, you have your improper affine spheres, and then you change coordinates and realize they realize them as Z2 singularities. Yes?
Yes.
So that was very interesting. That's very good. I enjoyed that.
I must say that the subject that I started here from Pedro and from Sidinia, and it has plenty of connection to the unknown mathematics for me, and mathematics, which is very interesting, and I never even dreamed that I will do it. So it is very interesting. Oh, sorry, I put here the Polish, I see now. Rysunek me in the picture. I don't know why I put it. This is in Polish picture. I'm sorry. rysunek. This. Now I know this. Sorry.
Okay.
Okay.
Thank you very much, Wojciech.
Thank
People
you. Thank
there
you.
are saying that your pictures are very nice, giving you congratulations. So thank you very much once again.
Thank you very much. Thank you very much. Thank you very much.
Hello. Our second speaker today is Professor Laurentiu Maxim of the University of Wisconsin. His title is Homological Duality, Jumping Loci, Propagation, Realization.
Hi, thank you for the introduction. I'm happy to be here. Do you hear me? Can you see me?
Yes.
Okay. First, I want to, of course, thank the organizers for inviting me. I came to Sao Carlos right after my PhD in 2006, and I still have very live memories from those days. This is my advice for junior mathematicians. Sao Carlos is the place to be, or the place to go to for singularities. So for junior people, this is the place where you bump into most singularity theorists you'll meet your whole life, your whole career. While for more senior people like me, for example, now this gives you an opportunity to get a broad overview and refresh of the singularity theory subject. So congratulations on the 30th anniversary in Sao Carlos, and I wish you energy and strength and motivation to continue for 30 more years at least. All right. So now back to my talk. So I'll talk about variants of Poincare duality for mainly complex algebraic varieties. We saw already in Dominic's talk yesterday a variant of Poincare duality theory for singular spaces. I'm happy that Clint introduced me because he has a lot to do with Poincare duality for singular spaces. What I will talk about today is a way of relaxing the duality conditions more in the spirit of Serre duality for projective varieties. And everything I will say today is joined to work with two very bright young mathematicians, Yunchan Liu and Botong Wang. All right, so I will start with some definitions from Beery and Ekman. These are built on prior work of Beery and Johnson and Wall. And eventually, everything has to do with studying algebraic varieties or CW complexes, if you like, through their covering spaces. An idea which goes back to Euler, Poincare, Abel, Shafarevich also did a lot of work in this direction in the context of complex algebraic varieties. So here is a definition from Beery and Ekman, or adapted from Beery and Ekman, of duality spaces. So a connected finite CW complex, let's call it X, with fundamental group pi, is a duality space of dimension n if, when I look at the cohomology of X with local coefficients in Z bracket pi in the group ring of the fundamental group with integer coefficients, this cohomology is trivial except in degree n, where it is torsion-free as a Z module. So here, Z bracket pi is regarded as local coefficients induced from the action of pi on Z bracket pi. All right, so in the compact setting, this can be formulated in terms of the universal cover of X as follows. If X tilde denotes the universal cover, then X is a duality space of dimension n, if and only if the cohomology with compact support of the universal cover with integer coefficients vanishes in all degrees except degree n, where it is torsion-free. So now you can imagine examples of such, and I give you here one, and I hope you think about this example a little bit, because later on I'll get back to this. So think of a closed oriented spherical manifold. So spherical means the universal cover is contractible, and let's say it has dimension n, then X is a duality space of dimension n. So this, to check this, you simply apply the remark just above it, which amounts to realizing this local system I put here in the definition in terms of a proper push forward or push forward with proper support from the universal cover. All right. This definition has been relaxed recently, or abelianized, so to speak, recently by Denham, Succio, and Uzvinsky, who instead of using the fundamental group, used coefficients in the group ring of the first homology group. Let's call it H. And they came up with this abelian duality space of dimension n notion, which means, just like before, that the cohomology of the CW complex X with coefficients now in the group ring of this first homology group vanishes except in degree n, where it is a torsion-free module as a Z module. Just as before, we remarked that if X is compact with a universal abelian cover X ab, so this is the covering space induced by the abelianization map, then X is an abelian duality space of dimension n if and only if the cohomology with compact support of this universal abelian cover vanishes except in degree n, where it is torsion-free. So an example I give you here is an n torus S1 to power n. This is an abelian duality space of dimension n. Of course, this is also a closed-oriented manifold, and it's an aspherical manifold, so it's also a duality space. But I put this example here because eventually I'm going to ask a question about it, so please keep this one in mind. All right, so now what is the purpose of introducing duality spaces and their abelian version? They enjoy duality properties, homological duality properties, similar to Serre duality for projective varieties. And as I said in the beginning, these are much less restrictive than Poincare duality. So let's give an example of some of these properties to see what I mean. So let's say if X is a duality space of dimension n, and I look at, let's call it D, the dualizing Z pi module. So this is the non-vanishing cohomology of X in degree n with coefficients in the Z bracket pi. So this is the only non-vanishing cohomology of X with these local coefficients. Then for any other pi representation of, call it A, the ith cohomology of X with coefficients in A is isomorphic to the homology in complementary degree of X with coefficients in D tensor A. So this is tensoring over Z. So this D really plays the role of the dualizing sheaf in Serre duality. Now, if D is just the integers with the trivial Z bracket pi action, then X is called the Poincare duality space. And these are the things that were studied previously, for example, in work of CTC Wall, whom I actually met, I think, for the first time at Sao Carlos. And furthermore, if X is a K pi 1 space, and these are in fact the cases considered by Bieri and Ekman in their paper in '73, such a duality space, which is a K pi 1, is simply says that the fundamental group pi is a duality group. Of course, you can say then you have a Poincare duality group and so on. All right, so let me start remarking before I give you some trivial or less trivial examples. Let me remark that the notions of duality and abelian duality spaces are independent of each other. So there are examples of in one class which doesn't belong to the other, which don't belong to the other. So one simple, very simple example comes from smooth complex projective curves, let's say of genus at least 1. So these are duality spaces, and it's very easy to check. These are compact, these are spherical. But among this, only elliptic curves, only genus 1 curves are abelian duality spaces. So here I gave you an example of something which is a duality space, but not an abelian duality space, say a curve of genus 2. And there are examples of, let's say, abelian duality groups, which are not duality groups, which I don't want to put on this slide, but you can find them, for example, in the work of Denham, Succio, and Uzvinsky. All right. Another interesting class of examples, which at least for what I care, motivated this abelian duality notion, comes from arrangements and their complements. So a linear arrangement is just a finite collection of hyperplanes in some complex affine space. A toric arrangement is a finite collection of codimension 1 subtori, possibly translated in some complex affine torus. And an elliptic arrangement is a finite collection of subvarieties in a product of an elliptic curve, each subvariety being a fiber of a group homomorphism from this product to the curve itself. And the theorem I'm going to state here has a somewhat long history, not necessarily in time, but with respect to the many groups of people who worked on it. So complements of all these kinds of arrangements turn out to be both duality spaces and abelian duality spaces. I will say more about this later on. I just wanted to put this here in the beginning as an example, as a motivating example. At least when I first heard about this problem, I think I heard the fact that people are interested in hyperplane arrangement complements, just the linear case being duality spaces or abelian duality spaces. All right, so we have a notion now. There is a natural question that one can ask: which spaces are duality spaces or abelian duality spaces? And I will stick to the simplest case, smooth real manifolds. Later on, I'll specialize even farther to complex algebraic varieties. But of course, you can ask this question in more general settings. And many things of what I say here can be extended farther, but I will not necessarily do that. I'll just present some basic cases here. So, as I said, I will talk mostly about complex algebraic varieties, and the things I'm going to use for this are cohomology, jumping loci, and the Albanese map. I should maybe say up front that even though I do not necessarily use the word perverse sheaf or perverse sheaves here, this is a talk about, or it's the consequence of working with perverse sheaves on very nice spaces. And I guess you already heard the word perversity in Dominic's talk. I'll only talk about the middle perversity here. And I think you heard about the word perverse sheaf in York's talk, though briefly. So let me start by saying what these ingredients are, what the cohomology jumping loci are first. So for a complex CW complex, a finite type with first Betti number positive, I define the character variety of X to be just complex characters of the fundamental group of X. And now to any such character, there is an associated rank 1 local system, which I denote by L sub rho. And I define the ith cohomology jump locus of X to be the collection of those characters of X for which the ith cohomology of the corresponding rank 1 C local system is not 0. These jumping loci have a long history. They appeared in work of Novikov, Ein Lazarsfeld, Green, Arapura, more recently Budur, Wang, and so on. And of course, Dimka, Papadima, Suchu. They have lots of applications in geometry, topology, algebra. Here I just give some applications to duality, as we'll see. The important thing about this is that about this jumping loci is that they are homotopy variants of the CW complex X I started with. So in particular, if I work with complex algebraic varieties, studying such jumping loci tells us a lot about the homotopy types of complex algebraic varieties. Some computational tools, immediate computational tools, the zeroth jumping locus. So if I look at the zeroth cohomology of this rank 1 local systems, they're all trivial except for the constant sheaf. And so the zeroth jump locus is just the point, it's just the trivial rank 1 local system. If I work with a closed-oriented manifold of real dimension n, then Poincare duality gives me a symmetry of this jump loci. So nu I of x is the same as nu n minus I of x. And finally, I want to mention here a very simple property of Euler characteristics, which turns out to be quite useful for calculations. If I have a character with associated rank 1 local system, call it R rho, then the Euler characteristic of x can be calculated from the cohomology of this rank 1 local system just by taking the usual Euler characteristic of this cohomology. Of course, in general, for a local system, you'd have to multiply the Euler characteristic of x by the rank of the local system. But here we work with rank 1, so we get an equality. So I want to give you some examples just to see how these properties work. So for example, if I work with a circle, then nu 0 is a point, the constant sheaf. Then Poincare duality tells me nu 1 is also the constant sheaf, and everything else has to be 0 by dimension reasons. If I work with the smooth curves I mentioned in the beginning of genus, let's say at least 2, then well, nu 0 and nu 2 are, so nu 0 is the constant sheaf, it's just a point, nu 2 is so just because of Poincare duality. But now let's take any character of x, and let's look at this cohomology. So, well, h0 and h2 are 0 for any character which is not a trivial one. And the Euler characteristic formula tells me that h1 cannot be 0. So the fact that the Euler characteristic is not 0 tells me that h1 of this rank 1 local system cannot be 0. So every rank 1 local system or every character is going to be in a nu 1. So nu 1 is the whole character variety. All right. So now I want to move to the topology of abelian duality spaces. Eventually, I will talk about duality spaces as well. But let me start with what I consider to be a simpler situation. We still have the situation of commutative algebra at hand here. So I'll start with a definition which gives the algebraic analog of jumping loci. If I have a Noetherian domain and a bounded complex of R modules with finitely generated cohomology, then to define jump loci for this complex, we choose a free resolution, a finitely generated free resolution of this complex, call it F. We tensor it with the residue field of various characters, and we look at characters or maximal ideals. We look at those maximal ideals for which the various cohomologies of this tensored complex is not 0. Okay, and the fundamental observation for us, from our point of view here, regarding jumping loci for abelian duality spaces is that they can be realized algebraically. So if I have an abelian duality space of dimension n, then I can realize nu I of x as nu I of this complex, which is, so now I work over C. This is the only non-trivial cohomology of x with C bracket H coefficients, H being the first homology group of x, but it's placed in degree n, so this is a shift here by minus n. In particular, can be seen from the above definition that nu I of x, so the jumping loci of such an abelian duality space of dimension n, are trivial, or the empty set in degrees higher than n. So now I have an algebraic realization of cohomology jump loci of an abelian duality space, and we can use since this C bracket H is a commutative ring, we can use commutative algebra to deduce the following properties. which we call the propagation package for abelian duality spaces. So first, and this is a result that was already obtained at the time of our work by Denham, Suchy, and Uzvinsky. First, if I have an abelian duality space of dimension n, then there is a propagation property, which can be stated as simply saying that this jumping loci form a nested sequence. So remember that above n I have nothing, is the empty set. So all available non-trivial jumping loci form a nested sequence. What we can get out of this algebraic interpretation is also the codimension lower bound for cohomology jump loci. So this says that for any index I non-negative, the codimension of, let's say, the jumping locus in degree n minus I. So this is just B1 of x. So B1 of x is the dimension of the character variety, which contains all these jumping loci, from which I subtract the dimension of the corresponding. So the codimension is the dimension of the ambient space, this character variety, minus the dimension of the jumping locus in degree n minus I. So this codimension is at least I. So what can we do now with these two properties? We combine them to get what in many instances was already known, this generic vanishing. So for example, if I choose a character rho, which is not in nu n minus 1, so nu n minus 1 has codimension at least 1, so its complement is going to be dense in the character variety. So if I choose a character in that complement, since the cohomologies of L rho in degrees from n minus 1 to 0 vanish, the only possibly non-vanishing cohomology of this L rho for generic character rho in the character variety minus this nu n minus 1, the only possibly non-vanishing appears in degree n. So for generic characters rho and all I not n, the ith cohomology of the corresponding rank 1 local system vanishes. So this is what's called the generic vanishing property. Now, from generic vanishing, if I take Euler characteristics, I told you the Euler characteristic of X is calculated from the Euler characteristic of any rank 1 local system. And let's say we choose a generic one, since all these cohomologies of L rho vanish except in degree, possibly in degree n. This tells me that we have what we call the signed Euler characteristic property, which tells us that the parity of the Euler characteristic of such an abelian duality space is really determined by the dimension n of the abelian duality space. Okay, and finally, let me state here another, which I think is a nice, interesting property, which we call the Betti property. So from the propagation property, we know that the constant shift is in all these jump loci, which means that the cohomologies in all degrees from 0 to n of the constant shift are not 0. So the Betti numbers of x between 0 and n are all not 0. So they're all positive. And moreover, if I apply, if I take I is equal to n in this codimension lower bound property, so B1 minus the dimension of nu 0 is at least n. This tells me that the first Betti number of x is at least n. So these are nice topological constraints on these abelian duality spaces. All right, so this package here gives you some constraints on abelian duality spaces, but they don't tell you what abelian duality spaces really are. So maybe let me state the propagation property first in the way I became aware of it. So this says that if I have a character for which the cohomology in degree I of this of the corresponding rank 1 local system is not 0, let's say I is some number between 0 and n, then all cohomologies between I and n are not 0. So this is a non-vanishing propagation. All right. So in the complex algebraic setting, we try to get more examples of abelian duality spaces, and I actually try to solve this realization problem via the Albanese map by using what I was saying earlier, properties of perverse sheaves on very nice spaces, which are the semi-abelian varieties. So I will try to remind people what these things are, and we take it from there. Then I give you more examples. So what are semi-abelian varieties? So first, let's start with abelian varieties. So an abelian variety of dimension G is a compact complex torus of dimension G. So you see G divided by a lattice of dimension 2G, which is also a complex projective variety. A semi-abelian variety, call it G, is an abelian complex algebraic group, which is an extension of an abelian variety by a complex affine torus. I will give you here a definition / example to any smooth. So there are many examples of semi-abelian varieties, and the way they come up is by this nice construction of the Albanese map and Albanese variety. To any smooth complex quasi-projective variety, one associates what's called the Albanese map. So this is a morphism from the variety X to some semi-abelian variety, call it alb of X, which is called the Albanese variety of X. So I will not maybe put a definition on the slide here, but you should think of the Albanese variety as being something like a minimal semi-abelian variety that X can map to, in the sense that there is a universality property saying that any morphism from X to a semi-abelian variety has to factor through the Albanese map. So as an example, if X is projective, then the Albanese variety is itself an abelian variety, and its dimension, its complex dimension, is half of the first Betti number of X. Okay. So now let's move to this realization problem, and or at least in the direction of the realization problem. First, I want to give more examples, or at least a more conceptual result that recovers the known examples of abelian duality spaces. And this can be obtained as follows. So if I have an n-dimensional smooth complex quasi-projective variety, which is homotopy equivalent to an n-dimensional CW complex. So for example, X is affine. Now I'm going to impose some conditions on the Albanese. So I'm asking that this Albanese is either proper and semi-small. I will not really define semi-smallness. This is something that has the property of preserving perversity conditions. But let me just give you examples here. A finite map or a closed embedding are such examples. Or the Albanese is quasi-finite. This is another possible property of the Albanese. So it's one or the other. For example, embeddings are quasi-finite maps. Then X is an abelian duality space of dimension n. So I put this n in color because the dimension of the variety, complex dimension of the variety, is a dimension of the abelian duality space also. And essential is this n in the middle, so that the variety should be homotopy equivalent to a CW complex of half its real dimension. So this affine situation is good for us, but as we'll see in examples, you don't need to have an affine variety to have this property. Okay. So this formulation can be made more general. You can of course have maps from X to some semi-abelian variety which satisfies some nice properties. And what you get at the end is even a relaxed version of a duality space. So what is behind this result? For I greater than n, the cohomology of this local system Z bracket H vanishes because X is the homotopy type of an n-dimensional CW complex. And to show vanishing in degrees below n, we rely on perverse sheaves. So we use perverse sheaves on the Albanese variety. And in fact, everything I stated here as conditions for the Albanese map guarantee that, let's say, if I work over a field, the push forward of the nicest perverse sheaf on the variety, on the smooth variety X, namely the constant sheaf shifted by the dimension, that the push forward of this nice perverse sheaf is also perverse on the Albanese variety. And they are using tools like the Mellin transformation, for example. And the universal coefficient theorem, we can conclude that the cohomology in degree less than n of this coefficient system Z bracket H is 0. All right. So let me show you how this result applies, right? So maybe I should move back. So I have an n-dimensional complex, smooth complex quasi-projective variety. It has the homotopy type of an n-dimensional CW complex, and the Albanese is supposed to be nice in the sense that it preserves this perversity properties. Though, of course, I'm not going to formulate it like this. Then we get abelian duality spaces. So let's see what nice examples of such things are. So let's first talk about very affine manifolds. So these are smooth closed subvarieties of a complex affine torus. And examples include essential linear or toric hyperplane arrangement. So essentiality means that the intersection of all these hyperplanes is 0-dimensional. Now, the closed embedding from X, such a very affine manifold, into the complex affine torus is being a closed embedding. This is proper and semi-small by definition. Hence, the Albanese itself, which factors this inclusion by the universality property, is also proper and semi-small. So X is affine, n-dimensional. The Albanese is proper and semi-small. So this tells us from the previous result that such very affine manifolds are example of abelian duality spaces. So now, from the propagation package for abelian duality spaces, I want to just remind you that there was a signed Euler characteristic property. So the parity of the Euler characteristic of a very affine manifold depends only on the dimension, right? So this was something that was observed by completely different methods by various people, and it appeared in algebraic statistics, so quite a different field in applied algebraic geometry. So these very affine manifolds appear there as algebraic models, as statistical models, and this signed Euler characteristic computes what is called the maximal likelihood degree of the respective statistical model. So people like Bernd Strumfeld or Junha and others worked on this, and this is a quite a nice example and quite important in applications. Other examples from what I mentioned earlier are these elliptic arrangement complements. So if I have an elliptic curve and I look at the complement of an elliptic essential arrangement in e to the n, call this complement X, then X is affine, n-dimensional, and by the universality property for the Albanese map, the embedding of X in e to the n factors to the Albanese. So the Albanese itself is quasi-finite, is 0-dimensional fibers. And this tells us from the previous theorem that X is an abelian duality space of dimension n. So this is a quick justification of the theorem I put on one of the first slides, in which I said that many people worked for quite some time on this. And finally, I want to give you an example that is not affine, but still of an abelian duality space. So let's say I have the blow-up of a two-dimensional affine torus at a point. Then the Albanese map is the blow-down map. And, well, this is proper and semi-small because of dimensionality issues. And it's a nice exercise to see that this blow-up is homotopy equivalent to a two-dimensional CW complex, more precisely the two torus wedge, a two-sphere. And then, well, by our result, X is an abelian duality space of dimension 2, but it's not, as we saw, it's not affine, right? It contains a projective line in it. All right, so the claim we made, which is still a conjecture, I think in one of our papers, is that if X is an n-dimensional smooth complex quasi-projective variety with proper Albanese map, then X is an abelian duality space of dimension n, if and only if the Albanese map is semi-small, and X is homotopy equivalent to a finite CW complex of real dimension n. So one can use properties of perverse sheaves to show. So this is like a converse to our theorem. One can use properties of perverse sheaves, like, I don't know, the decomposition theorem or the Harlefsh's theorem, to show that if you have an abelian duality space of dimension n in this setup, then the Albanese map is semi-small, but it remains to see. So right to left is what we already proved in the previous theorem, but from left to right, it remains to see that this you also need this finite this finite CW complex of real dimension n condition. All right, so now let me finally give an end result in the compact case. So I started with the realization problem for duality spaces or abelian duality spaces, and we saw earlier that we got results detecting abelian duality spaces, which certainly did not include projective varieties in them because of this homotopy type assumption. And now I want to actually give you a complete answer in the projective situation. So, or compact Keller situation. Let's say I have a compact Keller manifold. The X is an abelian duality space if and only if X is a compact complex torus. So these are very few. So in particular, abelian varieties, which are abelian varieties, well, these are abelian duality spaces, but they are the only ones, the only smooth complex projective varieties which are abelian duality spaces. And this can be, the proof is quite pretty, and this gives a complete answer to the realization problem for abelian duality spaces in the projective or Keller context. So here, first of all, so the propagation package is what is needed together with some other properties of perverse sheaves, let's say. So if X is Keller or projective of dimension, complex dimension n, the fact that it is an abelian duality space forces X to be an abelian duality space of dimension 2n. So it dictates the dimension of the abelian duality space. So this is the real dimension of X. Hence, from the Betti property for abelian duality spaces, the first Betti number is at least the dimension as an abelian space, or at least 2n. On the other hand, so I know that nu zero is just the point. So by Poincare duality, nu 2n, so the last non-vanishing jumping locus is also a point, and then propagation forces everything in between to be a point. So all these jumping loci for our abelian duality space are just points. This forces the Albanese map to be onto. So counting dimensions, this tells me that n is at least half of the first Betti number. So in fact, if I put 1 and 2 together, we see that the first Betti number of X is really 2n. So this the Albanese map is in fact onto and generically finite. With a little bit more work, it can be shown that it is in fact a finite cover, hence it is an isomorphism. All right. So this is the final answer for abelian duality spaces in the projective situation. All right, now, if you remember, I posted an example on one of the first slides in which I said that a real torus is an example of an abelian duality space. So now I'm asking, is there another example in the world of closed orientable manifolds, so which is not a real torus. So in other words, does this theorem, which I just present here, is this theorem valid in the smooth world? And this is my question, in case you have any insight in this. This should not be too hard to do, I guess. All right, so now I want to move to duality spaces. So I started with duality spaces of Beery-Ekman, but not much is known about their topology, and as we'll see, for a good reason. So what I want to do here is to give a few results and maybe at least a few open questions and tie it to other important problems in geometry and topology. So if X is a duality space, the question is, what can be said about this topology? So is there a corresponding propagation package, for example? So the first thing, I call it a theorem, but it's really just an observation following from Poincaré duality, is that if I have a closed-oriented manifold of real dimension M, then X is a duality space of necessarily dimension M, if and only if X is a spherical. So a spherical means, again, the universal cover is contractible. Now, even just looking at the sign of the, or the parity of the Euler characteristic of a duality space from this world of closed-oriented manifolds amounts to now answering the following question or conjecture of Zinger-Hoff, which says that if X is a closed spherical manifold of real dimension 2n, then the parity of the Euler characteristic is determined by n. So -1 to the n times the Euler characteristic is non-negative. So Hoff and Chern, I guess, stated this conjecture in the case of manifolds with a curvature condition, with negative curvature. And then Zinger extended this statement to spherical manifolds by using also, and there is an enhanced version of this conjecture by using a vanishing of L2 Betti numbers. So maybe I should say that the conjecture is true for Keller hyperbolic manifolds by work of Gromov, and Jost and Zuo prove it for Keller manifolds with non-positive sectional curvature, and their techniques are L2 techniques, so they really go into this Zinger formulation. Now, so it seems that the study of duality spaces is already related to a very big open conjecture in topology. But let's see what else can be said in this direction. So back to the complex algebraic world, as a remark, I'll just say that it can be seen from work of Demailly, Peternel, and Schneider that if you have a complex projective manifold for which the cotangent bundle is NEF, so numerically effective, so non-positive sectional curvature is one instance, then the Zinger-Hoff conjecture is true. So this is due to the fact that the Euler characteristic can be computed up to a sign as an intersection number, or the self-intersection number of the zero section in this cotangent bundle. And there are semi-positivity results for the Chern classes of NEF bundles in this work of Demailly, Peternel, and Schneider. And this tells you that indeed the Euler characteristic has the right sign in this case. So this numerical effective notion is something very important in birational geometry. The class of complex projective manifolds whose cotangent bundles are NEF is closed under taking products, subvarieties, and finite unramified covers. And it includes smooth subvarieties of abelian varieties. So these are very important examples. And you can think of it as some sort of degeneration of an ampleness condition. So for example, subvarieties of abelian varieties, smooth subvarieties of abelian varieties are have ample cotangent bundles, provided you have a large enough codimension. But for small codimension, this is not true. but nevertheless, these cotangent bundles are still Neff. So for line bundles, the Neff condition means simply that if you integrate the first, the Chern class of that line bundle along any curve, you get something non-negative. For an arbitrary vector bundle, there is a way to generalize this notion of Neffness by projectivizing the bundle and taking the Serre bundle on it and asking for that Serre bundle to be Neff. All right, anyway, so this tells us that this property of the cotangent bundle being Neff should be related somehow, or we hope is related to the property of the variety being aspherical. So we dare to actually make a conjecture in our latest paper stating that the cotangent bundle of any aspherical projective manifold is Neff. So this is really a daring conjecture. It's there is a possibility it's true. It would be nice. It would prove the Zingerhof conjecture, but we have some motivation for this. So it can be reduced to the following two conjectures, which identify the Steiness of the universal cover as a key property tying the geometry of the variety to that of the covering space. So this Steiness of the universal cover appears also in the Shafarevich conjecture. So first, the conjecture we made is that the universal cover of an aspherical projective manifold is Stein. So we could prove this provided that the Shafarevich conjecture is true. So for example, if the fundamental group admits a faithful finite dimensional linear representation. So this was a big case where the Shafarevich conjecture was true. The second conjecture in this direction says now it ties the Steiness of the universal cover to Neffness of the cotangent bundle. So it says that if X is a complex projective manifold whose universal cover is Stein, then this cotangent bundle indeed should be Neff. So there is some evidence in this direction due to Kratz, who show that this is true if this universal cover is the bounded domain in a Stein manifold. Not necessarily Stein, I mean, it's not the whole Stein thing, but it's a bounded domain and such. Okay, so I want to conclude with a list of references. So there are a few papers where these issues are discussed. As I said, this is a story about perverse sheaves. So many of these papers, most of these papers have perverse sheaves in the title. And I want to emphasize that this paper 4 here is the one that deals with these conjectures I mentioned on the previous slide. And this paper, in fact, deals with a more general question of Bavadia and Kolar about topology of maps to spherical manifolds. So I thank you for your attention, and again, happy 30th anniversary of Singularities in Sao Carlos.
Okay, to see if there are any questions. I have a expository comment. I'm impressed that you were able to give this talk without any use of perverse sheaves. That was kind of you.
Thank you.
I don't see any questions at this point. So thank you for a very nice talk, and everyone is invited to Web Coffee. You can find the link in your daily email.
Okay. Thank you again for the invitation, and I'll see you around.
All right.
Hello, everyone. Thank you very much for watching. Now I would like to announce the daily schedule for the rest of the day. So now in 10 minutes, there's going to be a web coffee, and you're all invited there. So please stay there for a bit, at least, just to take a picture of you all as well. Then at 11:40, there's going to be a gathering session. And the program is going to be as follows. Those of you who want to stay and chat about mathematics or whatever, you can stay in the room of the web coffee until 12:40. But those of you who would like to play some games, especially this called Gartic, there are going to be two rooms. The blue room, which is going to be an English version, and then the green room, which is going to be a Portuguese version. So you can choose depending on your choice. And the white room is, as we said, this for any chat is going to be the same link as the web coffee. At 2 o'clock, we start our parallel talks with Fernando Antonelli from Unifest, Brazil, who will speak about homeostasis, singularities, and input-output networks. And Maicon Varela from UFSCar, Brazil, who will speak about Newton polyhedra and Whitney equisingularity for isolated determinantal singularities. At 2:45, there's going to be the other two talks of the day, the final ones, from Miguel de la Rosa Castillo from Caniquit, Ujat, Mexico, who will speak about Kyogi-Saito-Hertling pairing as a bridge between Grothendieck and Poincaré dualities. And also Douglas Hilario da Cruz from Universidade Federal de Goiás, Brazil, who will speak about knots and asymptotic lines. Thank you very much and enjoy the rest of the day.